A compass needle rests in an open palm above a granite ledge somewhere in the field, its tip pointing not quite toward the horizon. There is a slight dip to it, a downward lean that has nothing to do with wind or the angle of the hand holding it. The needle is being drawn very gently toward the rock below, not dramatically, not with any visible urgency, just a quiet correction, as though the earth beneath the ledge has noticed the instrument above it and has something to add. This is not a malfunction. The compass is working exactly as it should. What it is working inside, however, is not the smooth, idealized planetary field that most navigational charts assume. It is inside a place where the rock has an opinion, and the rock's opinion is measurable. The Earth is magnetic at its most fundamental level. Deep in the interior, beneath the solid iron of the inner core and the rock mantle above it, there is a layer of molten iron and nickel in constant circulation. The circulation is driven by the heat flowing outward from the planet's core and by the rotation of the Earth itself, and the movement of this electrically conductive fluid generates an enormous magnetic field. The process has a name, the geodynamo, and it has been operating with interruptions and reversals for somewhere in the range of 3.5 billion years. The field it produces is not static. It shifts in strength and direction over decades and centuries, its magnetic poles drifting slowly across the Arctic and Antarctic regions, the whole invisible structure breathing at a pace too slow for any single human life to fully witness. The field extends far beyond the surface. It reaches outward into space, tens of thousands of kilometers from the ground, forming a region called the magnetosphere, which deflects the solar wind and shields the surface from a steady particle bombardment that would otherwise strip away the atmosphere in geological time. This is the large architecture. This is the planetary structure within which everything else sits. But the field is not uniform, and it is not simply a product of the deep interior. The surface itself contributes. Rock records the field. When molten rock cools and solidifies, the magnetic minerals within it align with whatever field exists at that moment, and then freeze in place, carrying that alignment forward through time. Magnetite is the most important of these minerals, an iron oxide with a strong affinity for magnetic orientation, and it is common in the igneous and metamorphic rocks that form much of the Earth's crust. In most places, the magnetic signal from the crustal rock is modest, a small addition to the ambient planetary field that instruments can detect, but that would not be obvious to anyone holding a compass. In some places, however, the crust contains enough concentrated magnetite, or enough rock with sufficiently strong remanent magnetization to produce something more conspicuous. The crustal field in these locations adds meaningfully to the field from below, or in some cases subtracts from it, creating what geophysicists call a magnetic anomaly, a departure from what the regional field alone would produce. The word anomaly carries a sense of wrongness that is not quite right for what is happening. Nothing has gone wrong. The field is doing what the field always does. It is the local geology that is different from the geology assumed in the smooth, averaged model that navigational instruments are calibrated against. The anomaly is not a problem with the field. It is a place where the field is more complicated than usual, and where that complication has been recorded in the rock and is continuing to express itself quietly in every compass brought near it. To understand what an anomaly is, it helps to have a sense of what the field looks like in quieter places. The field strength at the Earth's surface is not the same everywhere. It is weakest near the magnetic equator, roughly in the range of 25,000 nanoteslas, and strongest near the magnetic poles, where it approaches 65,000 nanoteslas. The nanotesla is the unit used in geophysical fieldwork, small enough to describe the fine variations in a field that is enormous in total extent. Between these extremes, the field varies smoothly with latitude, following broad patterns that geophysicists have mapped in fine detail. A navigator working with published tables can correct for the field's known variation without any instrument beyond a reliable chart and the date. Magnetic declination is a related phenomenon. It is the angle between the geographic North Pole, true north, determined by the axis of the Earth's rotation, and the magnetic north that a compass actually points toward. This angle is not zero at most locations on Earth, and it changes over time as the magnetic poles drift. In some parts of the world, it is small and barely matters for navigation. In others, it is large enough that an uncorrected compass heading can lead a ship or aircraft meaningfully off course. Published tables of magnetic declination allow navigators to correct for it, and these corrections have been available with varying accuracy for several centuries. Magnetic declination is a smooth, broadly predictable phenomenon. A navigator working with a good chart and a known position can account for it. A magnetic anomaly is something different. It is not a smooth latitude-dependent variation. It is an irregular departure from what the regional field model would predict, spatially confined, often abrupt at its edges, and not correctable with any general table, because it is caused by the specific geology of a specific place. Where a magnetic declination chart tells a navigator how many degrees to add or subtract from a compass reading to get true north anywhere in a given ocean, a magnetic anomaly chart describes the local effect of particular rock bodies on the field at particular locations. The two phenomena exist at different scales and require different tools to work with. The way geophysicists go about measuring anomalies has a particular quality of patience to it. A magnetometer is set up and carried across the landscape along carefully planned straight-line transects, on foot if the terrain requires it, or pulled behind a vehicle, or towed beneath a research aircraft, or mounted on a ship moving along a grid of survey lines. The instrument records the total field strength at each point along the transect. Back in the office, or in the field tent, the survey team then subtracts two things from their raw data. The first is the diurnal variation, the regular daily fluctuation in the field caused by the interaction of the solar wind with the magnetosphere, which can change the measured field by tens of nanoteslas over the course of a day, and which would otherwise appear in the data as a signal from the ground when it is actually a signal from the sun. The second is the reference field, the smooth, predictable component of the planetary field that a mathematical model can account for. What remains after both subtractions is the anomaly, the part of the measured field that comes from the rock below, stripped of everything else. The mathematical model used for this subtraction is called the International Geomagnetic Reference Field. It is a spherical harmonic expansion, a way of representing the global magnetic field as a sum of mathematical functions of increasing complexity computed from measurements made by ground stations, research ships, and satellites distributed across the planet. The model is updated every 5 years because the core field drifts, and a model computed from observations made between one update and the next will become progressively less accurate as time passes. Each version of the model has a validity period. After 5 years, the new data are folded in, the coefficients are recalculated, and the model is revised. It is a deliberate, unhurried process of collective measurement, computation, and revision, carried on by geophysicists at research institutions in a dozen countries. A surveyor working in the field with a magnetometer does not need to understand the mathematics of the model. What the model provides is a number, the expected field strength at any location on Earth, at any date, and the surveyor's measured number is compared against it. The difference is the anomaly value. In magnetically quiet regions, the anomaly might be a few tens of nanoteslas, barely distinguishable from instrument noise. In magnetically active regions, places with concentrations of magnetite-bearing rock, or thick accumulations of iron-rich geological formations, the anomaly can reach thousands or tens of thousands of nanoteslas, large enough that a compass brought into the area will behave noticeably differently from what its user expects. The image of anomaly that geophysicists work with most often is not a field sensation, but a map. When survey data are processed and gridded and rendered in color, the resulting image shows the ambient baseline in cool blues and greens. The Earth's ordinary magnetic personality spread across most of the map, and then in warm oranges and reds or in deep purples, depending on the color scale, the places where the crustal rock is producing something different. These warm zones are the anomalies. They correspond to buried ore bodies, to ancient intrusive rocks that have been covered by younger sediments, to volcanic formations, to old impact craters where deep material was excavated and recrystallized. Each one is a picture of what lies below. The surface may be flat farmland or open ocean, with no visible clue of what the rock beneath contains. The anomaly map reveals the hidden topography of composition, the contrast between magnetic and non-magnetic geology expressed in false color across a grid of numbers. To a geophysicist familiar with these images, they have an aesthetic quality. The smooth gradients of the reference field give way to tight, closely spaced contours where the anomaly intensifies. A compact, high-amplitude anomaly appears on the map as a tight cluster of warm colors, a bullseye of elevated field strength centered on whatever body of magnetized rock lies below. A broader anomaly, produced by a more diffuse concentration of magnetic material spread across a larger volume, shows up as a wide, gentle swell of elevated values across a large area. The shape and size of the anomaly on the map gives a geophysicist information about the geometry of the source, how deep it lies, how wide it is, how strongly it is magnetized. It is, in a quiet way, a form of seeing through the ground. What the color on the map represents at its most basic level is the behavior of a compass. In the cool blue regions, a compass needle in good working order will settle on magnetic north, the north predicted by the regional field, the north that published charts expect. In the warm regions, the compass will be drawn in a different direction. The amount of deviation depends on the anomaly's intensity and on the orientation of the source body below. It may be a few degrees, enough to matter in precise navigation, but not enough to be obvious from casual observation. It may be much more, 10 degrees, 30 degrees, or in the most extreme cases enough to cause a compass needle to point in completely the wrong direction, or to spin without settling, or to tip downward as though pulled by something in the ground. The compass needle resting in a palm above a granite ledge in the field, pointing not quite north, dipping slightly downward, this is the mild version of something that has much more dramatic expressions elsewhere. The downward dip of a compass needle is itself worth a moment's attention. A standard compass is built to show horizontal direction. It pivots on a vertical axis and swings in a horizontal plane to find north. But the Earth's field is not horizontal. It has both a horizontal component, which the compass needle responds to, and a vertical component which presses the needle either down into the earth or up away from it, depending on the latitude and the local geology. While near the magnetic equator, the field is nearly horizontal, and the vertical component is small. Near the poles, the field is nearly vertical, pointing almost straight down into the Earth at the North Magnetic Pole, and a compass needle, if it were free to tilt, would try to point at the ground rather than along the horizon. At mid-latitudes, the balance between the two components is intermediate, and a compass needle precisely balanced to swing freely in 3 dimensions rather than just 2 would show this. The downward lean of a needle above magnetite-rich rock is the vertical component of the local field being amplified by the rock below, pulling the needle toward the geology with an extra insistence that the standard horizontal plane instrument is not designed to fully express. The field is carrying information about the interior in every direction simultaneously. What a single compass needle shows is just one component of that information, the horizontal direction of the field at that spot, projected onto a circle. Geophysicists measuring anomalies want the full picture, the total field strength, and often the direction as well. And from these measurements, they work backward toward the geometry and magnetization of whatever lies below. This inversion problem, inferring the source from the measurement, is mathematically underdetermined, which means there is always more than one geological arrangement that could explain any given pattern of measurements at the surface. Experience and additional geological knowledge help constrain the possibilities, but the ambiguity is built into the physics. The field at the surface does not carry a complete and unique signature of the rock below. It carries a partial, ambiguous one that can be interpreted but not read directly. This is one of the things that makes the study of magnetic anomalies feel like a particularly patient science. The data are real, and the measurements are precise, but the thing being measured is always at a remove. The rock is below, the field is above. Between the two, there is a gap filled with inference, cross-checked against drill holes and seismic surveys, and the testimony of outcrops where the rock is exposed, gradually building toward a picture of what lies beneath, without ever fully closing the distance between the instrument and its subject. A geophysicist walking a transect, a straight line across a landscape, marked at intervals with flagging tape or GPS waypoints, pulling a magnetometer behind on a non-magnetic fiberglass sled, is engaged in this patient process. The choice of fiberglass is important. Steel or iron near the instrument would introduce a spurious signal, contaminating the measurement of what the ground below is doing. The sled is built to carry the instrument without disturbing it, to hold the magnetometer at a consistent height above the ground while the surveyor walks, to be dragged across grass and soil and gravel and low scrub without requiring the surveyor to carry the instrument in hand. The surveyor walks at a steady pace, watches the ground for obstacles, keeps the line straight by reference to a distant landmark or a compass bearing, using, with some care, the very instrument that the anomaly underfoot may be trying to mislead. At the end of the day, the data file on the instrument holds thousands of measurements, each attached to a GPS position, each representing the total field strength at a point on a line across a landscape. In the evening, the data are loaded into processing software. The diurnal correction is applied, using readings from a base station magnetometer set up at a magnetically quiet location nearby and left running through the day. The reference field values are subtracted. What appears on the screen is the anomaly grid, the Earth's hidden magnetic text, made visible by the subtraction of everything that could be accounted for without it. There is a particular quality to this kind of fieldwork that is easy to overlook when thinking only about the data. The field worker is walking through a landscape that looks like any other landscape: fields, outcrops, hedgerows, trees, soil, and beneath the surface, a geometry of rock is producing an invisible pattern of field variation that the instrument is reading continuously. The magnetometer makes this pattern audible in some configurations as a tone that rises in frequency with increasing field strength, a quiet acoustic display of what the ground below is expressing. The surveyor walks and the tone changes and the record grows, and the picture of the invisible will be assembled back at the desk from these accumulated footsteps across the ordinary surface. The International Geomagnetic Reference Field that the surveyor's data will be compared against is itself a remarkable object. It is not a physical instrument or a map in any conventional sense. It is a set of equations, a mathematical representation of the Earth's main field, derived from measurements made at hundreds of locations around the globe, updated every 5 years as the field shifts. The model captures the large-scale features of the field, the general increase in strength toward the poles, the tilt of the magnetic axis relative to the geographic axis, the broad geographic distribution of magnetic intensity. What it does not capture, by design, is the fine structure introduced by the crust. The model represents the deep field, the field generated by the geodynamo in the outer core, averaged and smoothed to remove the crustal contributions. This is exactly what makes it useful as a reference. By subtracting the model from a measurement, what remains is precisely the crustal part, the part the rock is responsible for. The model's equations are stored in a table of numerical coefficients, updated at each revision. A geophysicist in the field can carry these coefficients on a laptop or even a mobile phone, compute the reference value at any location and any date, and immediately know how far the measurement departs from the planetary average. The model is, in this sense, a global baseline, not a description of what the field is at any particular place, but a description of what it would be if the crust were magnetically neutral, if the rock below contributed nothing of its own. It is the planetary field stripped of local personality. Somewhere in a database maintained by institutions in several countries, the current set of coefficients for the International Geomagnetic Reference Field is stored and available for download. The equations it encodes represent the best current description of where the planet's magnetism should be, the smooth, averaged deep field architecture that underlies all the local variation. It is a model of the expected, a baseline for everything that departs from it. And somewhere in that departure, in the gap between the expected field and the measured one, in the warm colors on the anomaly map, in the needle that does not quite settle north, in the compass that dips slightly toward a ledge of granite, somewhere in that gap, the rock disagrees. Not loudly, not with any urgency. The rock does not announce itself. It simply carries, in its magnetite crystals, a record of the field as it was when the rock formed, 1 billion years ago, or 2 billion, or whenever the conditions were right for iron to precipitate from solution, or for lava to cool, in a field that has long since shifted, and it impresses that record, steadily and without ceasing, on every instrument brought close enough to feel it. The disagreement is patient and old and entirely without malice. It is the rock being what the rock is, a remnant magnetism persisting long after the circumstances that produced it have changed beyond recognition, holding its position in the field while the world above it and the field itself continue their slow drift. A compass needle set down on a table in a region of ordinary geology will settle quickly and hold its heading. The needle points at the horizontal component of the regional field, swings to rest, and stays there unless disturbed. The physics are simple and the result is reliable. Carry that same compass across country to a place where the crust contains a significant body of magnetized rock and the needle's behavior changes. It may settle more slowly, oscillating a little longer before finding rest. It may settle at a heading that is noticeably different from what the same compass showed an hour's walk away. It may refuse to settle reliably at all, drifting and drifting again as the instrument moves across a zone of strong gradient, where the anomaly's intensity changes over short distances. It may tip, the non-magnetic pivots that constrain a standard compass needle to a horizontal plane straining against the vertical pull of a field with a strong downward component. These behaviors are the surface expression of the geology below. The compass is reading something true. The needle is following the local field faithfully, tracking a variation that was not produced by any malfunction and that requires no supernatural explanation. The rock is present. The iron in the rock is magnetized. The magnetized rock produces a field. The compass needle follows the field. The whole chain is mechanical and documented and entirely amenable to measurement. What is interesting about it is not that anything is wrong, but that the field has so much fine structure, so many places where the local geology produces a departure from the smooth planetary average, and that this fine structure has been quietly shaping the behavior of every compass brought near it for as long as compasses have existed. The architecture of the field in its large sense has been in place for a very long time. The arching field lines that emerge from near the geographic South Pole and curve back into the planet near the geographic North Pole, the vast looping geometry that fills the space around the Earth and extends into the magnetosphere, have been present in one form or another through most of the planet's history, reversing polarity periodically over geological time, but always maintaining their general structure. This is the background against which every local anomaly exists. For the local field is always a modification of the global one, the crustal contribution riding on top of the deep planetary field, adding its particular signal to an already present baseline. A compass placed anywhere on the surface is reading both at once, the global and the local superimposed, the needle settling at a heading that reflects all of it simultaneously. The surveyor in the field with the magnetometer trailing on its fiberglass sled is walking through this superposition. The instrument records the total. The processing later separates the components. But in the moment of walking, the full field is what is present, the deep planetary structure, the slow drift of the magnetic poles, the broad variation with latitude, and then, if the geology warrants it, the extra component from the rock below, the crust speaking into the field it sits within. The map rendered in false color from processed survey data is a picture of that conversation, the crust talking, the planetary field as backdrop, the anomaly as the part of what the crust says that can be heard above the ambient signal. Blues and greens for the regions where the crust is quiet or where its voice is small relative to the planetary field. Warm oranges and reds for the places where the rock is speaking clearly, where the iron in the ground is concentrated enough to produce a signal that stands apart from everything around it. In these warm zones, the field is doing something the smooth model did not predict. The compass needle will behave differently there. The International Geomagnetic Reference Field will be updated again in a few years, its coefficients revised to reflect another period of slow drift in the core field. The planetary field will continue its patient change, the magnetic poles wandering across the polar regions as they have been doing for the whole of recorded observation and long before. The anomaly maps will be updated in turn, New survey data folded in, old datasets revised with more precise diurnal corrections and more accurate reference field subtractions, the picture of the crust's magnetic character becoming slowly more detailed, more confident, more fine-grained in its resolution. And beneath the survey grids and the false color maps and the mathematical model and the instruments on their fiberglass sleds, the rock will continue to do what it has always done. The magnetite crystals in the ancient iron formations, the remnant magnetization locked into the cooled volcanic rock, the fine-grained magnetic minerals in the deep metamorphic basement, all of it will continue to impress its field on the space above it, quietly, without interruption, at every hour of every day and night. A compass brought near it will feel the result. The needle will lean, or turn, or dip, following the local field faithfully, reading something real about the rock below. The model says what the field should be. The rock in certain places offers a different number. The difference between them is not a mistake. It is a fact about the Earth, a geological fact encoded in iron, persisting through time, available to any instrument sensitive enough to feel it. The International Geomagnetic Reference Field sits in its equations, quietly correct about most of the planet, updated every 5 years, a careful and accurate description of what the deep field provides. And somewhere beneath an ordinary stretch of ground, beneath wheat fields and open plains, and Arctic tundra and ocean floor, the rock disagrees with it, steadily and without hurry, and has been doing so since before the equations existed to describe what it is departing from. In Kursk Oblast, late on an autumn afternoon, the light comes in low across the wheat stubble and turns everything the color of old straw. The fields run flat to the horizon in every direction. There are no dramatic outcroppings, no visible seams of red rock, no surface feature that would distinguish this ground from 10,000 other agricultural plains across central Russia. A person driving through would see farm roads and grain silos and the ordinary geometry of land that has been worked for centuries. What they would not see, what no one can see, is that beneath this ordinary field, at depths ranging from a few hundred meters to several kilometers, lies one of the most magnetically intense concentrations of material anywhere on land. The iron ore body here is so vast and so rich in magnetized minerals that it reaches upward through the physics of the local field and announces itself through any compass brought near it. The needle does not simply drift, it argues. That particular quality of argument, the compass that does not merely err but insists on a different direction entirely, is what makes a magnetic anomaly zone different from the ordinary variation that navigators have always had to account for. The broader planet has a field. It runs broadly from south to north, curving through the interior of the planet in a pattern that has been roughly in place for billions of years, though not without interruption or drift. Any compass placed anywhere on Earth will point away from geographic north by some predictable margin, a margin that changes gradually as one moves east or west, and that geophysicists have mapped with enough precision to publish correction tables. A navigator can look up the expected deviation for any given location, apply the offset, and proceed with confidence. That is magnetic declination, and it is not an anomaly. It is a property of the planet, regular enough to be charted, smooth enough to be corrected for. A magnetic anomaly is something else. It is a place where the rock itself has its own opinion, where the mineral content of the crust, iron oxides, magnetite, certain basalts, and ultramafic rock types, has enough magnetic character to superimpose its own local field over the broader planetary one. The effect is not smoothly distributed. It does not fade gradually over hundreds of kilometers the way declination does. It has edges, it has a center, it has a gradient, sometimes steep, that a magnetometer walking across it will record as a sharp departure from what the regional model predicts. In the most intense cases, the departure is not subtle. The compass at the center of a strong anomaly is not pointing somewhere approximately wrong. It has been, in effect, captured by the rock below, and what it reads is the geography of that rock, more than the geography of the planet. These places are not rare. They are distributed across every continent and every ocean basin. They range from zones a few hundred meters across, the magnetic signature of a single magnetite-rich intrusion, to structures spanning hundreds of kilometers, where the geology beneath produces a field disturbance large enough to be detected by satellites. What they share is this: the crust is speaking, and the compass is listening to it rather than to the pole. The variety of reasons why the crust might speak, and how loudly, and in what direction, is where the story of magnetic anomaly zones becomes genuinely rich. The agricultural plain of Kursk Oblast, to stay with it a moment longer, sits above iron ore deposits that formed in a shallow Precambrian sea somewhere between 1, 8, and 2, 1 billion years ago. The chemistry of those ancient waters was different from anything in the modern ocean. Dissolved iron, released by volcanic activity, and the slow weathering of the earliest continents, combined with the oxygen just beginning to accumulate in the atmosphere through biological activity, and precipitated out in fine layers onto the seafloor. Over time, those layers became rock, dark and light bands, alternating, iron-rich and iron-poor, laid down with the regularity of annual seasons in a climate system that no longer exists. The rock that formed from those layers, banded iron formation, carries a magnetic memory of the conditions in which it cooled and solidified, and it carries that memory forward. 2 billion years later, lying under Russian wheat fields, it is still magnetically present, still organizing the local field around it, still redirecting any compass needle brought into its vicinity. The anomaly that formed above this deposit is the largest known on land. Its influence spreads across roughly 120,000 square kilometers, a territory larger than several European countries. At certain locations near its center, the measured field strength reaches values roughly 4 times what a compass in ordinary geology would experience. A needle placed flat on the ground within the core of the zone does not simply point a few degrees east or west of north. It may point south. It may tip downward at a steep angle, drawn by the intensity of the vertical component of the local field, as though the rock below is pulling it through the soil. Field geologists working in the most intense parts of the zone have long since stopped trying to use magnetic compasses for navigation. The instrument is not broken. It is simply too honest about what is below it to be useful for finding what lies ahead. That scale of magnetic character, the ore body speaking loudly enough to be heard 4 times above the ambient planetary field, is one end of the spectrum. The Bangui anomaly in the Central African Republic occupies the other end in a different way, where Kursk is a positive anomaly, a place where the field is stronger than expected. Bangui is a negative one. Near the center of this zone, which spans something on the order of 700 to 800 kilometers in diameter, roughly the distance between Paris and Berlin, the measured field values are weaker than the surrounding regional average. A compass there would not be dragged toward anything magnetic in the crust. It would be navigating, in a sense, with a slightly deflated version of the planetary field, the local rocks pulling the field downward rather than amplifying it. The rendered anomaly map of the African continent shows this clearly. The continent in magnetic false color is mostly warm tones, the measured field broadly following what the planetary model predicts, over ancient stable cratons and younger mobile belts. Near Bangui, a wide depression appears, a pool of blue at the center of an otherwise warm palette, its edges graduating slowly outward, the blue going to green and then to the ambient yellows and oranges of the broader continent. It looks settled in the map. It looks as though whatever happened there has been sitting quietly ever since. The cause of the Bangui anomaly is at present genuinely unresolved. One hypothesis holds that a large meteorite struck the region around 540 million years ago, fracturing and altering the local crust in ways that reduced its magnetic character and produced the pattern seen today. The hypothesis is consistent with some features of the anomaly's geometry and with what is known about the magnetic signatures of confirmed impact structures elsewhere. It is also consistent with some aspects of the local geology. It is not, however, confirmed. There is no undisputed impact crater at the site. The Bangui anomaly sits in the scientific literature as a question more than a conclusion, its edges carefully mapped, its center well documented, and its origin written in pencil rather than ink. There is something worth sitting with in that. A zone of 700 kilometers in diameter, detected from satellites, measured in detail across the central region of a continent, with a cause that cannot yet be stated with confidence. The scale of the uncertainty is not a failure of attention. Geophysicists have been aware of the Bangui anomaly for decades. The uncertainty is a property of the event itself. Something happened here long enough ago that the evidence it left behind has been compressed, buried, eroded, and overprinted by hundreds of millions of years of subsequent geology. What remains is the magnetic signal, which persists because magnetic minerals retain their character across deep time in ways that many other geological records do not. Across the Sahara, in the southwestern corner of Mauritania, a different kind of structure catches the light from space in a way that once made it a subject of considerable speculation. The Richat structure, sometimes called the Eye of the Sahara, is a geological dome approximately 50 kilometers in diameter, visible from orbit as a series of concentric rings of stone rising out of the flat desert floor. From a satellite image, it looks architectural, the rings too regular, the symmetry too deliberate, the scale too precise, and this quality of visual deliberateness led to decades of informal theorizing about what could have produced it. Impact events were proposed, unusual volcanic activity was discussed. The geology of the structure is better understood now. The Richat structure formed through a process of uplift and differential erosion operating over a very long time on Precambrian basement rocks, some of them dating back 600 million years or more. The dome was pushed upward, the overlying material eroded, and the resistant rings of harder rock were left standing, while softer material between them was carried away. The concentric geometry that looks so deliberate from orbit is a product of erosion respecting the circular symmetry of the original dome, nothing more unusual than that, at the largest scale of description. What is interesting in the context of magnetic anomaly zones is that the uplift of the Richat structure exposed basement rocks, including magnetite-rich intrusive bodies that carry their own magnetic character. The anomaly pattern across the structure is irregular, following the distribution of those intrusions rather than forming any neat concentric pattern of its own. A geophysicist walking outward from the center of the structure, magnetometer in hand, would record a sequence of field values that did not follow the visual symmetry of the rings above, but reflected instead the chemistry of the rock exposed by that erosion. A geologist standing at the center of the Richat, looking outward, sees the concentric ridges receding in every direction, a kind of stone bowl, ancient and wide, with the horizon punctuated by those regular lines of resistant rock. The magnetometer clipped to her belt is reading a value that differs from what the surrounding desert floor provides. The difference is not dramatic, not on the scale of Kursk, but it is real, and it follows the map of the intrusive bodies beneath her feet, bodies that were once deep inside the earth and are now, because of the slow work of erosion, near enough to the surface to influence an instrument in someone's hand. The Sahara sits still over these structures in a way that feels almost geological in itself. The stone rings of the Richat have been there since before there was a Sahara as such. They predate the current climate of the region by a very long time. The magnetic anomaly pattern across them has been there longer still. Both will be there, roughly as they are, long after any instrument currently measuring them has gone quiet. In the Atlantic, the geography of magnetic anomalies takes on a different character. The sea floor of the mid-Atlantic and the basins around it is geologically young compared to the ancient cratons of Central Africa or the Precambrian formations of Central Russia. The ocean floor is created continuously at mid-ocean ridges, where the tectonic plates pull apart and fresh basaltic magma wells up and solidifies. As it solidifies, it records the direction of the ambient planetary magnetic field at the moment of cooling, a magnetic snapshot of what the field was doing when the rock formed. Because the planet's field reverses periodically, the seafloor carries a record of those reversals in alternating bands of normally and reversely magnetized basalt, spreading symmetrically away from the ridge in both directions. The field above this seafloor is consequently striped with alternating positive and negative anomalies, zones where the ancient basalt is adding to the current field direction, and zones where it is subtly opposing it. Parts of the western Atlantic, including the waters that map broadly to the area known as the Bermuda Triangle, overlie this kind of seafloor geology, along with the magnetic signatures of volcanic seamounts scattered through the basin. The navigational history of the region, the reason certain cultural narratives attach themselves to these waters, is genuinely complicated by a magnetic fact that has nothing to do with the unusual seafloor geology. The agonic line, the line along which magnetic declination is zero, runs through the western Atlantic. This means that compasses in those waters aligned close to true north rather than pointing east or west of it, as navigators along most other coastlines expected. A navigator calibrating instruments based on experience in European or Caribbean waters, where declination ran reliably east or west, arriving in waters where it was near zero, might interpret the compass as behaving strangely when it was, in fact, behaving correctly. The confusion was real, historically documented, and entirely explainable, without reference to anything unusual about the seafloor. A 16th century navigator, pausing at the bow of a caravel, somewhere west of the Canary Islands, watching the compass settle on a bearing that has shifted since the previous morning's reading, writes the discrepancy into the log with care and without explanation. He does not know whether the shift is the needle or the world. The notation is precise, the handwriting practiced, the observation accurate. What he is recording is not mystery, but measurement, a measurement whose cause he cannot yet account for, because the tools for accounting for it will not exist for several centuries. The same waters, measured now with the instruments available, produce anomaly maps that are detailed and well explained. The mystery was in the absence of information, not in the field itself. The Oregon vortex near Gold Hill sits in the Klamath Mountains of southwestern Oregon, in terrain underlain by ultramafic rock types, serpenite, peridotite, that formed in the deep ocean and were thrust onto the continental margin over millions of years through the slow collision of plates. These rock types are among the most magnetically interesting in terms of their ability to carry remnant magnetization, a record of past field conditions imprinted into the mineral structure of the rock itself, which can persist and exert influence on nearby instruments regardless of what the current planetary field is doing. A compass placed within the area of the Oregon vortex reads differently from one placed 30 meters down the slope. This difference is real, and it is measurable, and its cause is geological. The site became a tourist attraction in the early 20th century and continues to draw visitors who report experiencing disorientation, apparent violations of gravity, and visual effects in which objects appear to roll uphill or in which people appear to change height in ways that contradict expectation. These perceptual effects are consistently explained by the geometry of the structures on the site. Buildings and platforms set at angles to the true slope of the hillside, producing visual reference frames that mislead the perceptual systems calibrated to expect horizontal floors and vertical walls. The inner ear and the visual system, when they disagree about what is level, produce disorientation reliably, and a sloped structure inside which all visible lines are tilted from true will do this to nearly any visitor. The magnetic anomaly and the perceptual effects are two separate phenomena occupying the same location, each with its own explanation. A compass left on a wooden post inside the Oregon vortex enclosure reads several degrees differently than 130 meters away and below it. This is the part that is geological. The sensation of stepping down a slope that appears to run upward is the part that is visual. Both are real. Neither requires any explanation that exceeds what the physics and geometry of the site provide. The serpenite in the hillside was emplaced there by plate tectonics, and it is doing what serpenite does in the presence of a compass. The tilted structure is producing optical illusions because tilted structures do that. The two facts coexist without any need to blend them into a single unified story, and both are more interesting in their separation than they are when combined. The Klamath Mountains in which the Oregon vortex sits are geologically complex, a collage of terranes, fragments of old ocean floor and island arc material that have been accreted to the North American margin over hundreds of millions of years. The ultramafic rocks of the area are part of that accretion, former pieces of ocean floor that ended up on a continent. Their magnetic properties reflect the history of their origin, the field conditions under which they cooled, the metamorphic events that overprinted some of that magnetization, the current ambient field that they are neither fully obeying nor fully resisting. A magnetometer carried through the Klamath Mountains records a magnetic texture as varied as the rock itself, quiet in some areas, disturbed in others. The field above the ultramafic bodies, stepping up or sideways from what the planetary model would put there. Geophysicists who study remnant magnetization in ultramafic terranes use the Klamath region as one of a number of field locations where the magnetic history of old ocean floor can be read directly. The rocks carry, encoded in their mineral structure, information about where on the planet they formed, what the field was doing when they cooled, and how they have been heated and stressed since. Reading that information requires instruments sensitive enough to detect differences of a few nanoteslas, and analysis careful enough to separate the ancient record from the noise of the current field. The compass on the wooden post inside the tourist enclosure is not doing any of that analysis. It is simply responding to the vector sum of everything magnetic in its vicinity, and in the Klamath Mountains above Gold Hill, that sum is somewhat different from what the planetary model alone would produce. All 5 of these places, the wheat fields above Kursk's iron ore, the wide blue depression over Central Africa, The eroded dome rings of the Saharan Richat structure, the striped basaltic seafloor beneath the western Atlantic, the ultramafic hillside in southwestern Oregon share the essential quality of a magnetic anomaly zone. The crust has its own contribution to make, and where the crust speaks loudly enough, the compass listens to it instead of to the pole. The variety of causes is as wide as the variety of ways geology can concentrate or alter magnetic minerals. Ancient banded iron formations, possible meteorite impacts reworking the chemistry of the crust, uplifted basement rocks carrying magnetite-rich intrusions, young mid-ocean basalts recording ancient field reversals, old ocean floor thrust onto a continent and retaining the magnetic memory of its origin. Each mechanism produces a different anomaly geometry, a different pattern on the false color map, a different behavior in a compass placed within it. What they share too is this: they have been here for a very long time, operating quietly, and only relatively recently has any instrument existed that could detect and describe them with precision. The Kursk anomaly was large enough that military surveyors noticed it through compass deviations in the 1870s. The Bangui anomaly was first identified from aeromagnetic surveys in the 1950s and 1960s. The magnetic texture of the Richat structure has been studied in detail only since airborne and satellite geophysical surveys became routine enough to cover remote desert terrain systematically. The anomaly maps of these places are recent documents. The anomalies themselves are not. There is something particularly easy to rest with in that thought, at least in the late hours. The planet has been carrying these magnetic signatures for millions and billions of years. The fields have been there over every period of human history, present under every civilization that occupied ground near them, operating through every navigation attempt made in waters above them, felt by every creature whose biology uses the magnetic field to orient and move. The crustal rocks beneath Kursk were laid down before there were animals with bones. The geometry of the Bangui Depression formed, if the impact hypothesis is correct, before there were plants on land. The seafloor spreading that produced the striped magnetic pattern beneath the Atlantic has been proceeding since long before anyone crossed those waters on any kind of vessel. The instruments that can read these fields in detail, the airborne magnetometers, the satellite sensors, the sensitive ground-based fluxgate, and proton precession instruments, are the newest thing in the entire picture. The fields are old, the rocks are old, the anomalies have been present and precise the entire time. The survey grid comes last, drawn across terrain that has been magnetically characterful since before the terrain itself had its current name or shape. A magnetic anomaly survey rendered in false color, the kind of map that hangs in geophysics laboratories or appears in journal articles as a figure, compresses all of that time into a single image. Blues and greens for the areas where the crust is quiet and the field approximates what the planetary model predicts. Warm oranges and reds where the rock below is contributing something additional, pulling the measured values above the baseline. Cooler colors again, sometimes purple, sometimes a different kind of blue, where the local geology reduces the field below the regional average, as at Bangui. The color transitions on these maps can be gradual, the field fading slowly across tens of kilometers of transition zone, or they can be abrupt, a sharp gradient at the edge of a highly magnetized intrusive body, where the field steps up several thousand nanoteslas within a horizontal distance that could be walked in minutes. Both kinds of boundary are interesting. The abrupt ones are where the compass behaves most dramatically. Standing at one of those abrupt boundaries, magnetometer in hand, a field geophysicist can watch the reading change as she walks forward. 10 meters to one side of the boundary, the reading is consistent with the regional model. 10 meters to the other side, it has risen by enough that the compass is pointing somewhere demonstrably different from where it was pointing before she crossed that invisible line in the soil. The line itself is geological. It corresponds to an edge in the rock below, a contact between magnetic and non-magnetic material, a fault that has juxtaposed different rock types, or a dike that has intruded into the surrounding formation and is now announcing itself by its magnetic character. The line is not marked. There is no visible change at the surface. Grass grows on both sides. Wind moves across both sides. The anomaly boundary is entirely invisible and entirely real. This is the basic texture of a world that has a hidden magnetic geography, a geography that does not show itself to the eye, that leaves no topographic signature in most cases, that can only be read by instruments sensitive to field variations below the threshold of any human sensory system. The false color maps are translations of this geography into something visible. They are the first view most people have ever had of a landscape that has been present all along. The 5 zones described above are among the ones large enough or interesting enough to have attracted sustained study. They are not representative of the full range. Magnetic anomalies exist over submarine volcanoes that have never been surfaced, over deeply buried ore bodies that have never been mined, over impact structures whose surface expression has been completely erased by erosion, but whose crustal signature persists. They exist over metamorphic terrains where ancient rocks have been reheated and remagnetized in the deep crust. They exist beneath polar ice sheets, mapped by airborne surveys that fly predetermined grids over terrain no instrument has otherwise touched. The full magnetic map of the planet's crust is not yet complete, and the survey work that would complete it is ongoing. The International Geomagnetic Reference Field, the mathematical model against which all anomaly measurements are compared, is updated every 5 years by a collaboration of researchers from institutions across many countries. Each update incorporates new satellite data, new ground-based observatory readings, and new analysis of the secular drift in the planetary field, the slow change in the field's overall structure that results from ongoing fluid motion in the outer core. The model is, at any given moment, the best available description of what the planetary field should be doing everywhere on Earth. It is a mathematical description stored in coefficients, validated against observation, and used as the baseline from which every anomaly measurement is calculated. The anomaly is the difference between what the model predicts and what the instrument records at any particular location. The model, by construction, represents the planetary field, the smooth, broadly distributed component generated deep in the planet. What it does not contain is the crustal contribution, the magnetized rocks, the old ocean basalts, the iron ore bodies, the serpentite terraneans, the frozen record of ancient field reversals. That contribution is the anomaly, and it is, in its totality, a second magnetic map of the planet, a map not of the planetary interior, but of the mineral history of the crust itself. The Richat structure, from low orbit, shows its stone rings catching the Saharan light in the long shadows of a low sun. The concentric ridges are pale against the darker material between them, an arrangement that from above looks very much like the kind of target an enormously patient and extremely old process might have drawn across the desert floor. The magnetic anomaly associated with it follows no such neat geometry. It is irregular, patchy, responding to the actual distribution of the magnetite-rich intrusives exposed by the dome's erosion. The visual elegance and the magnetic reality are different shapes laid over the same terrain. That mismatch is not a failure of either to conform to the other. It is simply a record of the different ways that different processes, leave their marks on a piece of the Earth's surface. The magnetic personality of the Richet structure has been recorded in maps and in datasets. The interpretation of those datasets continues to develop as the techniques for separating different components of the anomaly signal are refined. The stone rings will be there when the interpretation is updated. They will be there when the instruments that measured them are long retired. They will be there when the Saharan climate cycles through whatever configuration comes after this one. The magnetic intrusives beneath the ridges will be there too, oriented as they are, carrying the memory of whatever the field was doing when they cooled, still capable of redirecting a compass placed in their vicinity, quietly decoding themselves into the datasets of anyone patient enough to walk the transect lines and record the numbers. In the winter of 1874, Ernst Lenz sat at a desk somewhere in St. Petersburg with a stack of survey reports from the military cartographers working the fields south of Kursk. The reports described a needle problem, not a small drift, not the ordinary declination that any navigator learns to subtract before plotting a line, but a sustained, repeatable, significant displacement, compass needles in a certain region of Kursk Oblast, pointing not toward the north, but toward the east-southeast, settling there as though they had decided, and holding that position without trembling. Lenz set down the stack and wrote a formal account of what the instruments were doing. He did not know yet what lay beneath the fields. He knew only that the needles were telling him something, and that whatever they were telling him was consistent and large and real. The instrument readings that troubled Lenz were coming from a landscape that offered to the eye almost nothing unusual. Kursk Oblast in the 19th century was agricultural country, flat and wide, given to wheat and rye and the long open horizons that come with that kind of terrain. Surveyors moved across it in the ordinary way surveyors did, compass in hand, chain behind them, marking the land in sections. The problem they reported was not dramatic in appearance. A needle pointing east-southeast instead of north does not announce itself as a geological discovery. It looks at first like a faulty instrument. It was only when every instrument brought to the same location produced the same reading, and when moving 20 kilometers in any direction allowed the needle to swing back towards something more expected, that the pattern became undeniable. Something beneath the surface was asserting itself through the soil and into every magnetic instrument within a very large radius, and the assertion was calm and steady and enormous. What lay beneath the fields was iron, not surface iron, not an outcrop or a vein, but iron in quantities that required a different order of thinking entirely. The banded iron formations under Kursk and its neighboring oblasts were laid down between 1, 8, and 2, 1 billion years ago in shallow Precambrian seas. The process that created them was slow and chemical. The gradual oxidation of dissolved iron in ancient ocean water as the first significant oxygen-producing organisms began releasing gas into an atmosphere that had never held it before. The iron settled out in thin layers, alternating with silica-rich chert, building up over millions of years in fine horizontal strata, the way sediment builds, season by season, at the bottom of still water. Each layer was a small event in a chemistry that ran for an unimaginable span of time. The result, compressed and buried, and eventually uplifted into the shallow crust beneath what would one day be a Russian wheat field, was one of the largest iron ore deposits ever found on land. A core of banded iron formation pulled from a borehole in 1923 would have shown those layers clearly, dark and light, alternating in fine striations, the iron bands carrying a reddish-brown quality in certain lights, the chert between them paler and harder. The layers are often only a few millimeters thick, and in places they run for hundreds of meters without interruption, carrying the regularity of something laid down by a process that did not vary much for very long periods. There is something in the look of them that sits oddly with human intuition about old things. Old things are usually worn, irregular, uncertain at their edges. These layers are neither. They are precise. They are horizontal. They have the quality of a record made by something that had no reason to be imprecise, in a time before there was anything around to observe whether they were or not. And the iron in them is still magnetically active, 2 billion years after it settled, still carrying the orientation it was given when it crystallized in a sea that no longer exists under a sky that bore no resemblance to this one. It was bore holes, not lenses account, that finally confirmed what the compasses had been indicating for decades. In 1923, drilling near what would eventually become the city of Gubkin struck high-grade iron ore at depth, and the abstract problem of the needle deviation resolved into a concrete geological reality. The ore was not only present, but abundant, so abundant that subsequent surveying of the region eventually characterized the deposits beneath Kursk, Belgorod, and Voronezh oblasts as holding reserves in excess of 25 billion tons. The anomaly zone covering those deposits extends across approximately 120,000 square kilometers, a continuous region roughly the size of a small European country, all of it subject to the magnetic influence of the iron below. The word anomaly is worth sitting with for a moment. In geophysics, it means only a departure from what the regional field model would predict, not a flaw, not an error, not a malfunction. The field in Kursk is behaving exactly as physics says it should behave, in the presence of a very large quantity of magnetite and ferromagnetic minerals at shallow crustal depth. The anomaly is not the ground misbehaving. It is the ground speaking, very clearly and very loudly, in a frequency that compass needles happen to be perfectly designed to hear. The planet's average field in that latitude would be somewhere in the range of 50,000 nanoteslas. At certain locations within the Kursk anomaly zone, measured values reach 193,000 nanoteslas. The field at those points is roughly 4 times what a compass is calibrated to expect. A compass placed flat on the soil of a Kursk wheat field and left to settle would not, in the anomaly's core zone, point anywhere that a navigator trained on ordinary declination charts would recognize as north. It might point southeast. It might tip its north-seeking end downward toward the ground at a steep angle drawn by the strong vertical component of the local field rather than by the horizontal component that makes compass navigation useful. In some locations within the anomaly's more intense zones, the needle oscillates rather than settles, not because the field is variable, but because it is so much stronger in the vertical direction than the horizontal that the needle cannot find a stable equilibrium in its housing. The instrument is not broken. It is working. It is simply receiving information the instrument was not built to hold. Field geologists working within the core of the anomaly know to leave their magnetic compasses in their bags. This is not an emergency procedure or a special precaution. It is simply a practical acknowledgement that the tool is not useful here. In its place, surveyors have used celestial observation, reading the sun's position, to determine direction the way navigators did before magnetic compasses existed. They have used landmark triangulation, identifying fixed points in the landscape and calculating bearing from their geometry. And in more recent decades, they have used GPS, a technology that routes its directional information through orbital satellites rather than through the local field, and is therefore indifferent to what the iron below might prefer. The anomaly, in this sense, is not an obstacle, it is a circumstance, and like most circumstances, it has practical responses. What the anomaly does to a compass depends partly on where within the zone the compass is. The anomaly is not uniform. It has gradients, regions where the field intensifies toward its maxima, and regions where it relaxes. Its influence can be detected at distances of hundreds of kilometers from its center, though at that range the deviation a navigator would notice is subtle enough to fall within the range of ordinary declination correction. Moving inward, the effect grows. A compass that is off by 2 degrees at 400 kilometers might be off by 30 degrees at 100, and might fail to find a stable resting point at all within a few kilometers of the most intense zones. A series of measurements taken along a transect moving toward the center of the anomaly would show a number that climbs at first slowly, and then, within the final tens of kilometers, rapidly, the way temperature climbs when approaching a source of heat, and what's parabenefactaft, though the thing doing the climbing here is invisible, and the source is buried beneath hundreds of meters of rock. A geophysicist in the 1930s, sitting at a field table somewhere in the oblasts with a stack of anomaly maps spread before them, would have seen this gradient expressed as contour lines. Contour lines on an ordinary topographic map are spaced according to terrain, widely separated on flat ground, crowded together on steep slopes. Contour lines on a magnetic anomaly map follow the same logic, but the thing being measured is field strength rather than elevation, and what a crowded contour map of the Kursk anomaly shows is not a cliff, but an intensity. Near the edges of the zone, the lines are spaced comfortably. Closer in, they press together. At the center, in the earliest maps, the contours crowd so tightly they nearly overlap, each one a line connecting points of equal field strength, all of them stacked close because the field rises steeply toward its maximum over a short horizontal distance. The maps from that period have a quality to them that is both technical and at the same time somehow legible as a portrait of something large and concentrated lying just below the surface. Soviet industrial attention arrived in the 1950s. Open pit mines were established near Gubkin and Zheleznogorsk, two cities that grew in large part from the mining operations themselves. The Lebedynsky mine near Gubkin became one of the largest open-pit iron ore mines in the world, its excavation eventually reaching a depth of several hundred meters and a width measured in kilometers. The strata of banded iron formation exposed in the pit walls during those years were visible in cross-section, the same layers that had settled in Precambrian seas, now standing in a vertical face, their horizontal regularity running across the exposed rock in bands of red and pale gray, each band a distinct layer from a different moment in an ancient chemistry. Standing at the edge of such a pit and looking down at the exposed strata is to see geological time made visible in a way that is almost architecturally legible. The bands are so regular and so clearly horizontal that they look less like natural formation than like something laid course by a process that understood what it was doing. By the late Soviet period, the Kursk Basin was producing tens of millions of tons of iron ore annually, and in producing it, the mining operations generated something else of considerable scientific value, one of the most detailed geomagnetic datasets ever compiled for any single location on Earth. Geophysicists working the region over decades took measurements along systematic transects, documented the anomaly's behavior with depth and distance, compared readings against international reference models, and produced maps of the underground iron structure that could not have been made any other way. The anomaly, in this sense, paid for its own study. The same iron that was bending compass needles across half of Western Russia was, when properly mapped, providing a three-dimensional portrait of its own shape and extent that geophysicists in any other terrain would have required far more invasive methods to obtain. The needles that had confused lenses surveyors in 1874 were, a century later, the starting point for some of the most detailed subsurface iron ore mapping ever attempted. The scale of the anomaly requires some time to settle into. 120,000 square kilometers is not a region one drives through in an afternoon. It is not a valley, not a mountain range, not a county. It is larger than most European countries, and it is all, in some proportion, magnetically influenced by the iron below it. Moving through that landscape in an ordinary car, on an ordinary day, nothing indicates that the ground beneath the road is remarkable. The wheat fields look like wheat fields. The roads are flat. The horizon in that country is very far away and very level, and the sky above it is large. Nothing about the visible landscape announces what the subsurface contains. The anomaly is invisible to everything except instruments designed to measure it, and the animals, and the occasional plant whose growth patterns are subtly shaped by the unusual conditions in the soil. The field is there regardless of whether it is being measured. The range of effects a compass experiences within different zones of the anomaly is worth tracing carefully. At the outermost perimeter of the anomaly's influence, a well-calibrated compass, held by someone who knew the standard declination for that region, would simply show a reading slightly different from the published chart correction, and the difference might fall within the instrument's ordinary margin of error. Moving inward, the discrepancy grows. At some intermediate distance, the needle's north-pointing end begins drifting toward the east or southeast, away from the geographic north it nominally seeks. Still closer in, the deviation becomes large enough that it would be recognized immediately as abnormal by anyone who had used a compass before. 30 degrees, 40 degrees, the needle resting at an angle that has no relationship to the direction of the magnetic pole that navigation depends on. In the most intense zones, the needle may point south, or oscillate without settling, or tip sharply downward, drawn by the vertical component of the field rather than the horizontal. The same instrument, at each of these distances, is functioning correctly. The field it is measuring simply changes with location in ways that a standard compass, designed for a standard field, was not built to express legibly. There is something worth pausing on in the fact that the iron causing all of this was laid down in Precambrian seas that bear no relation to any geography that currently exists. The continents looked different then. The coastlines were different. The atmospheric composition was different enough that the oxygen-producing chemistry that precipitated the iron from seawater in the first place was itself a radical development, a transformation of the planetary atmosphere that preceded the anomaly's creation and made it possible. The shallow sea that held the original iron ore in the region that would eventually become Kursk Oblast was gone long before the first recognizable animals existed anywhere on Earth. The rock above it shifted, and the sea filled in with sediment, and time accumulated above the iron in quantities that are not easy to hold in mind. 2 billion years of additional geological history proceeded above those banded layers, entirely indifferent to what was being preserved below. And when Russian military surveyors walked onto that land in the 19th century with their compasses, the iron was still there, still carrying its magnetic orientation, still registering in every instrument sensitive enough to respond to it. A thought that arises naturally in this context, and that bears quiet attention, is that the iron's magnetic orientation was set when it crystallized. Magnetite and other ferromagnetic minerals acquire their magnetization at the moment of formation, aligning with whatever field is present at the time. The field that the Kursk ore was magnetized in was Earth's magnetic field as it existed approximately 2 billion years ago. Different in strength, different in polarity, different in its precise direction than what geophysicists measure today. This remanent magnetization, the magnetization retained from the original formation, is part of what makes the anomaly so strong. The iron is not simply responding to the current field. It is also contributing its own historical magnetization, locked into its crystal structure from a different magnetic era of the planet. The anomaly is, in a certain sense, a record of a field that no longer exists, still legible to instruments in the present, still persistent enough to redirect every compass brought near it. This is the quality that gives the Kursk anomaly a particular kind of depth when considered slowly. It is not simply a large deposit of a common mineral. It is a deposit of iron that has been magnetically active for 2 billion years, without interruption, carrying an orientation that was set in conditions that no living thing witnessed, expressing that orientation in measurements that geophysicists can compare against their models and find deviating significantly from what the models expect. The iron does not know this. It simply is what it is, doing what the physics of ferromagnetism requires it to do, indifferent to the surveyor's confusion and the geophysicist interest, and the miner's equipment, and the accumulated decades of study that have been applied to it. It was there before Lenz's report. It was there before Russian military cartography existed. It was there long before anything walked on the land above it. And on the days when no one is measuring anything in Kursk Oblast, it is there still, quietly reorganizing every compass brought within a certain radius of its center, not out of any intention, but simply because that is what 2 billion years of magnetized iron does. Soviet geophysicists working the Kursk region after the ore discovery produced datasets of considerable richness, and part of what they documented along the way was how the anomaly behaves with depth. Surface readings give one picture, airborne measurements give another, because at altitude, the anomaly's signal has spread and smoothed, the sharp gradients near the surface reduced by the intervening air. Deep borehole measurements give a third, because at depth, the instrument is closer to the source and the field is correspondingly stronger. Integrating these three perspectives, surface, aerial, and subsurface, produced a three-dimensional map of the iron's distribution that could not have been assembled from any single vantage point. The anomaly, seen in 3 dimensions, has structure. It is not a uniform mass, but a complex body with its own internal architecture, regions of higher and lower grade ore, zones where the formation is thicker or thinner, areas where faulting has displaced the original layers. The contour maps that show it in 2 dimensions are a simplification of something that has depth and volume and a specific shape within the crust, a practical detail that gives some sense of the anomaly's reach. The instrument geophysicists use to measure it, the magnetometer, can detect deviations of a nanotesla or less, with some modern instruments resolving differences at the fraction of a nanotesla level. The Kursk anomaly, at its center, produces readings of 193,000 nanoteslas in a world where the global average is somewhere around 50,000. This is not a measurement that requires a sensitive instrument to notice. It is a reading that a relatively crude magnetometer would register without difficulty, and it is a reading that an ordinary compass needle, which is much less sensitive than any electronic magnetometer, will respond to unmistakably. The anomaly is large in area, extreme in intensity, and old in origin. Those three qualities together make it something that is difficult to characterize adequately in ordinary terms, not because it resists description, but because the description, when accurate, contains numbers that require some effort to situate in felt reality. There is a quieter kind of scale to the anomaly, though, alongside the geological and numerical one, it is the scale of its age relative to anything else on the surface of the land above it. The wheat that grows in Kursk Oblast is an annual crop, replanted each year. The farmers who plant it are present on a time scale of decades. The roads and buildings of the cities above the ore body have existed for centuries at most. The ore body itself has been known in the scientific sense for a century and a half, and the ore within it and the field it generates has been there for 2 billion years. Setting those timescales alongside each other is one of those exercises that resists completion, the way it is difficult to hold the size of an ocean fully in mind, even when you are standing at its edge and looking out over it. The intellectual knowledge that the figure is large does not automatically produce the felt sense of how large it is. What does produce it sometimes is staying with the image of the field, continuing without interruption, not pausing, not varying, not diminishing in any meaningful way over geological time, while the surface above it underwent every kind of transformation that 2 billion years of planetary history can produce. The open pit mine at Gubkin offers one of the places where the anomaly becomes most physically tangible in something other than instruments. At the edge of the pit, looking down into it, the exposed face of the banded iron formation runs across the rock wall in horizontal strata that extend further than the eye can comfortably follow in either direction. The individual bands vary in color, red and rusty, where the iron is concentrated, pale gray or cream, where the chert predominates, and in thickness, from a few millimeters to a few centimeters. At the scale of the pit wall, which may be hundreds of meters high, in the deepest sections, the bands run from one edge of the visible rock face to the other without interruption, carrying the horizontal regularity of their original deposition despite the billions of years between their formation and the morning light now catching them. In the early hours of the day, when the low sun rakes across the exposed rock at an angle, the bands cast small shadows in the shallow depressions between layers and stand out from one another with particular clarity. The red bands and the pale ones run across the face of the pit wall like a very long sentence written in a language that no one speaks, but that magnetometers and compasses and the nervous systems of certain migrating animals are well equipped to read. The question of what the anomaly does to the immediate landscape beyond the needle behavior has been studied from several directions. One area of interest has been whether crops growing in anomaly zones show any measurable differences from those growing in adjacent regions of ordinary field strength. The evidence on this point is mixed and not settled, and the difficulty of isolating the magnetic variable from the many other soil and atmospheric variables that affect plant growth makes the question genuinely hard to answer cleanly. What is clearer is that the soil chemistry over iron-rich bedrock differs from soil chemistry over other rock types, and some of those chemical differences affect plant growth independently of any magnetic effect. The two influences are difficult to separate. Research in the region has continued for decades, and the dataset accumulating from it is one of the more detailed pictures of a single anomaly zone's effects that geophysics and agricultural science have between them produced. Animals passing through the anomaly zone are in a different position than instruments because their magnetic sense, where it exists, is not simply a compass. Birds that navigate magnetically are responding to inclination and intensity, as well as direction, and the Kursk anomaly alters all three. A migratory bird crossing the zone on a southward autumn passage would encounter a field that is stronger than expected, with a steeper inclination angle and a horizontal direction that may depart significantly from the ambient regional field. What the bird does with that information depends on how its navigation system weights its magnetic sense against its other navigational inputs: star patterns, sun position, polarized light, learned landmarks. The degree to which the anomaly actually disrupts bird migration through the Kursk region has not been thoroughly documented in the published literature, and the honest answer is that it is not well known. What is known is that the anomaly provides the conditions under which disruption would be possible, and that birds using the regional field as their primary navigational reference would have different information within the zone than outside it. Whether they respond to that difference, and how, is a question that belongs to ornithology as much as geophysics. By the late Soviet period, and continuing afterward, the Kursk Basin had become one of the most studied geomagnetic environments on Earth, not because of its navigational complexity, but because of its economic importance and its scientific legibility. An anomaly this large and this intense provides a natural laboratory for understanding how crustal magnetic signals relate to the underlying geology. The datasets compiled there have been used to test and refine methods of magnetic interpretation that have since been applied to prospecting in other regions, the Kursk anomaly serving, in a sense, as the calibration standard against which subtler anomalies elsewhere can be understood. A method of interpreting a magnetic gradient that works correctly at Kursk, where the signal is unmistakable, can be trusted to work at smaller scales where the same physics applies, but the numbers are far less dramatic. What Lenz noticed in his stack of reports in 1874 was not the anomaly in its geological fullness, because that fullness was not yet available to anyone. He noticed only that the needles were doing something unexpected in a consistent and spatially organized way, and he described that observation formally. The boreholes of 1923 confirmed the cause. The decades of Soviet industrial and scientific work extended the picture into 3 dimensions and into the historical depth of the geological record. And the anomaly itself, across all of that time, continued doing what it had been doing since the iron crystallized in Precambrian waters, generating a field deviation large enough to redirect every compass brought within several hundred kilometers of its center, strong enough to tip needles downward at steep angles in its most intense zones, old enough to have been in place before anything, with a nervous system evolved, the capacity to be confused by it. On a quiet morning at the open pit mine near Gubkin, in the hours before the working day's machinery takes over, the exposed strata of banded iron formation in the pit walls sit in the early light, without any audience. The red bands and the pale ones run horizontally across the rock face, their regularity unhurried, their depth reflecting the thickness of the iron's original deposition in a sea that ended before the Cambrian began. The field the iron generates moves upward through hundreds of meters of overlying rock and sediment, invisible and unimpeded, into the open air above the pit and across the wheat fields beyond it, and outward for hundreds of kilometers in every direction, declining with distance, but never quite disappearing within the region the anomaly has claimed. A compass brought to the pit edge would not find north. A compass 50 kilometers away would find something close to north, but not quite. A compass 400 kilometers away would show the anomaly's influence only as a faint residual, barely distinguishable from ordinary declination. The signal still present, but reduced to something that requires careful measurement to separate from the background field. And beneath all of it, the iron continues its work, not work in any intentional sense, but the quiet, consistent, entirely impersonal assertion of 2 billion years of magnetized Precambrian ocean chemistry, still gently reorganizing every compass brought near it, as it has been doing since long before there were any compasses or any human hands to hold them. William Austin Burt set down his standard compass in a clearing in Michigan's Upper Peninsula sometime in 1844 and watched the needle do something it was not supposed to do. It did not settle toward north, it pulled toward the ground. The iron ore beneath the soil of that forest was close enough to the surface that the instrument in his hand had effectively stopped working as a compass and started working as a kind of imprecise metal detector, pointing at the earth rather than at the horizon, faithfully responding to the strongest magnetic field it could detect, which was not the planet's distant core, but the rock lying just below the roots of the trees around him. Burt had been running survey lines through that terrain for 3 days. The work of the General Land Office required him to produce accurate township boundaries, the kind of boundaries that would eventually determine where property lines fell, where roads could be built, where legal ownership would begin and end across thousands of square kilometers of forested land. Every one of those boundaries depended on a compass reading. Every one of those readings, he now understood, had been quietly wrong. The iron in the ground had been redirecting his measurements by degrees he could not calculate without knowing precisely where the ore was, which he also did not know. 3 days of careful work had produced a survey that agreed with itself but did not agree with the actual cardinal directions of the world outside the anomaly. He looked at the compass. He looked at the clearing. Somewhere below the forest floor, a body of iron ore lay in the rock, carrying its own magnetic field, adding its voice to the planet's larger signal until the sum was something different from what any standard chart would predict. It was not a mystery in the troubling sense. The compass was working. It was simply answering a different question than the one he needed it to answer. The problem was not with the instrument. The problem was with the assumption that the instrument's answer and the direction north would always be the same thing. What Burt did next was not to abandon the survey or to despair at the days of work that would need to be redone. He sat with the problem the way a practical person sits with a practical problem, turning it over until a solution appeared. The solution he arrived at was to stop asking the earth where north was and to start asking the sun. The solar compass he developed and patented the following year was a brass instrument that used the angle and position of the sun, in combination with the date and the local time, to establish true north without any reference to the planet's magnetic field at all. It pointed skyward rather than earthward. It answered to astronomy rather than to geology, and in doing so, it bypassed entirely the invisible interference that lay beneath the trees. The Michigan surveys that had been corrupted by the Lake Superior iron ranges were eventually resurveyed using the new instrument. The boundaries that emerged from those corrected surveys were accurate in the way that the original readings could not have been. The ore that had caused the problem was later understood to be part of one of the richest iron-bearing geological formations in North America, the kind of deposit that would eventually underwrite the steel production of an entire industrial era. In the 1840s, standing in that clearing, Burt knew none of that. He knew only that the needle was pointing at the wrong thing, and that a man who wanted to know where he was would need to look somewhere other than down. The surveyors who worked the Lake Superior ranges were not the first people to notice that certain landscapes seemed to hold opinions about where north should be. Portuguese navigators sailing south along the West African coast in the middle decades of the 15th century had been making notes in their logs about compass behavior that refused to conform to expectation. The coast they were mapping was geologically young in some stretches, underlain by the kind of volcanic and igneous rock that carries strong remnant magnetization, rock that was once molten, that cooled and solidified with the magnetic field of the moment, frozen into its crystals. As a caravel worked its way past a headland of basalt or a coastal shelf of iron-bearing stone, the compass needle would shift by a degree or two, and then shift back, and the navigator keeping the log would note the discrepancy without necessarily understanding its cause. Near the Canary Islands, near the Azores, near the Cape Verde archipelago, these variations were particularly noticeable. All three island groups are volcanic, not ancient, cooled, and deeply weathered, but geologically recent, built from successive eruptions that pushed magnetite-rich material up through the ocean floor and into the air. A navigator who had calibrated his compass in Lisbon Harbor and then sailed south for 3 weeks would find, somewhere in those Atlantic waters, that the reading no longer matched what his charts predicted. The needle had shifted, the discrepancy was real, and the explanation available to a 15th century Portuguese sailor working at the outer edge of the known world, without any concept of crustal magnetic anomalies or remanent magnetization, was that something in the water was interfering with the instrument. Some navigators of that period wrote of magnetic mountains in the ocean. Others attributed the deviations to divine influence, to the proximity of the equatorial regions, where, in the cosmological thinking of the time, the natural order of things might be expected to behave differently. A few simply noted the numbers without comment, the way a careful person notes any data they cannot yet interpret, writing the degree of deviation in the margin, placing a question beside it, trusting that the accumulation of observations would eventually produce something like an answer. What they were recording, though they had no name for it, was what later centuries would call magnetic declination, the difference between compass north and true north, and in those island waters, a layer of anomalous crustal magnetism was adding itself to the standard declination, producing deviations that no general chart of the period could have predicted. The islands were not cursed, the water was not magical, the rock beneath the ocean was old and strongly magnetized, and it was doing what magnetized rock does, which is to contribute its own field to whatever field was already present. The same way a voice added to a chorus does not change what the others are singing, but changes what the room hears. By the time European navigation had expanded to cover most of the accessible ocean, the accumulation of compass deviation records was substantial enough that some navigators had begun to understand the phenomenon in at least practical terms. A ship that had made a particular passage several times knew from experience where the compass could be trusted and where it could not. The knowledge was passed from pilot to pilot, encoded in sailing directions, added as marginal notes to charts that were already covered in the accumulated observations of a century of voyaging. This was not the knowledge of a theory. It was the knowledge of repeated encounter, the kind of understanding that precedes explanation and sometimes outlasts it. In the waters around Iceland and the Faroe Islands, where young volcanic geology produces some of the most irregular magnetic anomaly patterns in the North Atlantic, navigators of the 17th and 18th centuries had already noted compass deviations of 20 to 30 degrees from the values their charts predicted. An Icelandic coastal pilot of that era would have known, through years of working those waters, that the compass in a particular stretch of coastline near a lava headland could not be relied upon in the way it could be relied upon elsewhere. The knowledge lived in the body rather than in any instrument. The angle of the swell, the color of the water over a submerged shelf, the particular quality of light on a familiar shoreline in certain weather, these were the navigational tools that supplemented and sometimes replaced the compass needle in waters, where the compass needle had its own ideas about direction. Maritime historians examining the distribution of shipwreck sites in the North Atlantic have noted a statistically suggestive relationship between clusters of wrecks and zones of elevated magnetic field gradient near Iceland and the Faroe Islands. The wrecks in question are mostly from the 17th and 18th centuries, a period when oceanic navigation had grown ambitious enough to make distant passages routine, but had not yet developed the instruments that would make those passages reliably safe. Dead reckoning, the method by which most navigators of that period established their position, depended on a chain of calculations in which each link had to be correct for the whole to remain sound. Compass heading, speed through the water, time elapsed, leeway from wind and current. The position estimate that emerged from these calculations could be held with confidence only as long as the inputs were accurate. In waters where the compass was reading several degrees east of true north, the heading was wrong. The position calculated from that heading was wrong, and the coastline that appeared out of the dark or the fog was not where the chart said it should be. The Scilly Isles sit at the southwestern tip of England, a cluster of low granite islands and rocky shoals extending into the Atlantic shipping lanes. Granite is not, in general, a strongly magnetic rock, but the geological history of southwestern England involves episodes of mineralization that have left pockets of iron-bearing material distributed through the regional geology in ways that are irregular and not always predictable from surface observation. The waters around the Scillies are shallow and treacherous in ways that standard charts of the early 18th century did not always adequately represent. And on the night of October 22nd, 1707, a British naval squadron under the command of Admiral Sir Cloudesley Shovel was making its way northeast through those waters in the dark, returning from operations off Gibraltar. The squadron's navigators had been calculating their position throughout the voyage. The consensus in the chart room was that the ships were safely to the west of the Scilly Isles, with open water ahead. The rocks arrived 40 minutes after that assessment was made. 4 ships of the squadron struck the islands and their outlying reefs. Between approximately 1,400 and 2,000 people were lost. Admiral Chauvel did not survive. The inquiry that followed was a careful one, in the way that 18th century naval inquiries were careful, thorough within the limits of what was then known, and genuinely interested in preventing the same thing from happening again. The navigation had failed. The primary cause identified was failed dead reckoning. The squadron had lost accurate track of its longitude across a long ocean passage, and the position its navigators believed they held was not the position the rocks confirmed. And the variable magnetic properties of the granitic geology of southwestern England, and the degree to which those properties may have contributed small but compounding errors to the compass headings on which the dead reckoning depended, were not factors that the inquiry could quantify with the tools available in 1707. What the disaster contributed to was an urgency around the longitude problem, the long-standing navigational crisis of not being able to determine, at sea, exactly how far east or west a ship had traveled. The marine chronometer that eventually resolved this problem developed over the following decades through the work of several instrument makers, allowed navigators to compare the local time aboard a ship with a known standard time and calculate from the difference exactly where, in terms of longitude, they were. It was not a compass replacement. It was a second instrument answering a different question, the way Bert's solar compass answered a different question than the standard needle. The sea had produced problems that a single instrument could not solve, and the solution, in both cases, was to find a second reading that did not depend on the first. The miners and surveyors who worked the iron ranges of Michigan, Wisconsin, and Minnesota in the 19th century accumulated their own body of practical knowledge about compass behavior in magnetically anomalous terrain. William Bert's encounter with the problem in 1844 led to the solar compass and to a formal acknowledgement that the region's geology made standard magnetic survey impractical. But the ore that had deflected his needle continued to deflect the needles of everyone who came after him. The Lake Superior Banded Iron Formation, as geologists later named it, is one of the largest bodies of iron-bearing rock in the world, laid down in a shallow Precambrian sea and then folded, faulted, and partially buried by subsequent geological events over the course of nearly 2 billion years. A surveyor walking a standard township line across its surface was not just walking through forest, he was walking across the top of a geological archive of almost incomprehensible age, and the archive was speaking in the only language it had to every instrument sensitive enough to hear it. The General Land Office surveys conducted over the Lake Superior Iron Ranges before Bert's intervention produced township grids that did not agree with each other or with the true cardinal directions they were supposed to encode. The errors were not random, they were systematic in the way that errors produced by a consistent but unmeasured force are always systematic, all displaced in a direction that corresponded to where the ore was thickest, where the local magnetic field was strongest, where the compass was most confidently pointing at the wrong thing. The resurveys that corrected these boundaries, using the solar compass and later using astronomical observation, produced property lines that looked different on a map from the ones they replaced, and the renegotiation of those boundaries took years. There is something in this that is worth sitting with for a moment. The Earth was not doing anything unusual. The iron ore was behaving exactly as iron ore behaves. The magnetic field it produced was a predictable consequence of its mineralogy and its history. The problem was an assumption, the assumption that anywhere on the surface of the continent, in any geology, in any terrain, the compass would be pointing at the same thing. It was a reasonable assumption in most places. It was wrong in that place. And the wrongness was not visible on the surface of the land in any way that a person walking through the forest could detect. The trees looked like other trees. The soil looked like other soil. The sky above the anomaly zone was identical to the sky above the normal ground outside it. Only the needle knew, and it was not explaining itself in any language that a surveyor in 1844 had the conceptual vocabulary to read. The World War II period introduced a new class of navigator to the problem of magnetically anomalous terrain, the airborne navigator, working at speeds and altitudes that compressed the consequences of a compass error in ways that ground-based survey work did not. An aircraft following a heading that is wrong by 5 degrees covers the relevant distance from expected position much faster than a surveyor on foot. A navigator over the Kola Peninsula in northern Russia, flying a mission into the Arctic, was working over terrain that geologists of later decades would describe as one of the most heavily mineralized landscapes on Earth. The Kola Peninsula and the surrounding region of northwestern Russia and adjacent Scandinavia sit atop vast bodies of iron and nickel ore, intruded through ancient Precambrian basement rocks and carrying strong magnetic anomalies across thousands of square kilometers of territory. Allied air crews flying over this region during wartime reported compass unreliability. The instruments behaved differently from what the mission plan assumed they would. Post-war analyses of Arctic operations attributed some navigational errors to the magnetic anomalies of the underlying geology, though in the conditions of wartime flying, over territory only partly mapped, in weather that frequently obscured both sun and stars, with instruments that were sometimes imperfect and always affected by the magnetic fields of the aircraft itself. It was rarely possible to isolate any single cause with the precision that a peacetime investigation might achieve. What those navigators had in common with the Portuguese sailors on the West African coast 3 centuries earlier, and with the General Land Office surveyors in Michigan, and with Admiral Chevel's navigators on their fatal approach to the Scillies, was that they were all working with an accurate picture of the magnetic world as it should be in a standard place, and they were in a place that was not standard. The charts they carried described the field that a model of the Earth would predict. The field that their instruments were measuring was the sum of the model field plus whatever the local geology was contributing. That sum was different from the prediction, and the difference compounded across a night passage or a long survey line or a darkened bombing run over mineralized terrain was large enough to matter. The navigational response to this problem in each era followed a similar pattern. First, the accumulation of evidence that something was wrong, compass readings that did not agree with position, surveys that did not close, headings that produced unexpected arrivals. Then the search for a cause, constrained by what the era knew about the Earth's magnetic field and how it worked. Then, sometimes, the development of a workaround, a second instrument, a different method, a local knowledge practice that substituted experience for theory, and eventually, in the modern period, the mapping of the anomalies themselves, so that the difference between the predicted field and the measured field could be charted and corrected for, the way the difference between magnetic north and true north had been charted and corrected for centuries earlier. The geophysicists who mapped the Lake Superior Iron Ranges in the 20th century produced some of the most detailed aeromagnetic surveys ever conducted over North American terrain. Aircraft flying systematic transects, each parallel to the last, each at a constant altitude, carrying sensitive magnetometers and recording field values at intervals of a few hundred meters. These surveys produced maps of magnetic intensity that showed the ore bodies not as they appeared from the surface, which was as ordinary forest and agricultural land, but as they were underground, rendered in the false colors of varying field strength, the ore showing up in deep reds and oranges against the cooler blues of the surrounding granite. Bert's problem, the problem that had pointed his compass at the ground rather than at the sky, was now visible from the air, mapped, measured, and filed in the archives of the United States Geological Survey. Those same surveys produced something useful beyond the mapping of the ore. They produced a record of the difference at every surveyed point between the field the International Geomagnetic Reference Field model predicted and the field the instrument actually measured. That difference, the residual, as geophysicists call it, is the anomaly itself, not the total field, not the predicted field, but the gap between them. Charted across a landscape, those gaps tell the story of the geology below. They describe where the crust is rich in iron minerals, where it contains other magnetic materials, where ancient intrusions of volcanic rock have been emplaced and then buried by later deposition. They are, in a sense, a map of the past written in the present. the geological history of the region expressed as a pattern of magnetic deviation that instruments can read, even when the surface gives no sign of what lies beneath. The practical consequence of this kind of mapping for navigation is that the anomalies become known. A modern pilot flying over the Kola Peninsula carries charts that account for the magnetic properties of the terrain below. A modern surveyor working over the Lake Superior iron ranges uses GPS, which does not ask the Earth's magnetic field for directions at all. The problem that defeated Bert in 1844 and that corrupted surveys across a generation of township work has been solved, in the practical sense, by instruments that root around it entirely. But the anomalies themselves remain. The ore is still there. The field it produces is still there. Every compass brought into that territory still answers to that field. The geological fact has not changed. What has changed is that the geological fact is now legible. The deviation that seemed, to a surveyor in the forest, like an arbitrary failure of an instrument that should have been reliable, is now understood as information, as a reliable signal about an unreliable substrate, a consistent message about the specific character of a specific piece of ground. The compass that points southeast in a Kursk wheat field, or that pulls toward the forest floor in a Michigan clearing, or that shifts a degree from the previous morning's reading in the waters near the Canary Islands, is not malfunctioning. It is reading the field that is present. The field that is present is not the field the model would predict. The gap between them is the anomaly, and the anomaly is, in its patient and entirely impersonal way, telling the truth about the rock below. The Portuguese pilot who noted his compass deviation in the margin of his log and placed a question mark beside it was doing the same thing as the geophysicist who subtracts the reference field from the measured field and studies what remains. Both were in the presence of a difference they could measure. Both were uncertain about what was producing it. The pilot carried no theory adequate to the observation. The geophysicist carries one. And yet the observation itself, the needle not where it should be, the reading not matching the prediction, is the same observation in both cases, separated by 5 centuries of instrument development and theoretical framework, but identical in its essential character. This is, perhaps, the quietest way to think about what magnetic anomalies represent in the history of human navigation. They are places where the Earth was always doing something specific, something consistent, something that followed rules as regular as any other physical process, and where human instruments, arriving with assumptions calibrated elsewhere, found themselves in the presence of a local truth they had not been designed to expect. The Earth was not being unhelpful. The iron ore in the ground of Kursk Oblast, or the Upper Peninsula of Michigan, or the seafloor near the Faroe Islands, was simply being iron ore, doing what iron ore does, which is to hold its magnetism and to share it with whatever field passes through it. The navigators and surveyors who encountered these places were skilled at their work. They were using the best instruments available. They were applying the best methods their training had given them. And they were wrong in specific ways, in specific places, because the ground beneath them had not been consulted when the charts were drawn. Bert's solar compass is now in the collection of the Smithsonian Institution. It is a beautiful instrument, brass and glass, carefully fitted, the kind of object that shows the attention of a maker who understood that the thing being built would need to be trusted absolutely by the person using it. It was designed to work in places where the standard instrument failed. It was designed around the recognition that some ground cannot be asked for magnetic directions, and that the sun, which does not concern itself with what the ore deposits would prefer, will tell the truth about direction, regardless of what the rock below has to say. In a Michigan forest clearing, in the afternoon light of the mid-19th century, Bert held this instrument and pointed it not at the earth, but at the sky, and the survey line it produced ran true. North is north, east is east, the townships falling into their correct places on a map that would eventually describe the legal boundaries of a landscape over which iron ore sat in the ground in quantities that made the whole earlier navigation problem seem, in retrospect, like a reasonable price to pay for the eventual knowledge of what was there. The brass catches the light, the sight lines align with the sun. The needle in the solar compass is not a needle at all, it is a shadow cast by the sun's position across a graduated scale, pointing at a direction the earth has no power to alter. The deviation below, the ore and the field it generates, continues quietly, doing what it has always done, and the survey line runs straight regardless, because the man holding the instrument decided, at some point in 1844, in a clearing in Michigan, to stop asking the ground where north was, and to ask the sky instead. The sky in this regard has always been reliable. The sun rises east and sets west, and at noon it is south of every point in the northern hemisphere, and these facts are not subject to the opinions of the geology below. A compass that depends on the earth must accept what the earth has to offer. An instrument that depends on the sun gets the same answer everywhere. In that small difference between an instrument that reads the field that is present and an instrument that reads the position of a star lies the history of a practical problem and a practical solution. Worked out in a forest clearing, in a place where the iron in the rock had been quietly reorganizing every reading taken above it for as long as anyone had been taking readings there at all. The solar compass sits in its glass case, well preserved, still legible, as the thing it was made to be. Outside the Smithsonian's walls, the magnetic anomalies of the Lake Superior iron ranges continue to deflect every compass brought across them. The field they produce has not weakened since the Precambrian sea that laid down the ore evaporated from the surface of the planet. It will not weaken in any time scale that matters for navigation. The same force that pulled Bert's needle toward the forest floor is pulling at every compass brought there now, steady and indifferent, pointing at what it finds rather than at what a navigator might prefer to find. The solar compass, open in the afternoon light in a forest clearing, points at the sun instead. The survey line runs true. The iron below continues its long, patient misdirection, speaking in the only language it has, to every instrument sensitive enough to hear. A European robin is sitting on a low branch at the edge of a forest in Germany, in the last slow light of an October evening. The branch is thin, the bird is small. Around it the other forest sounds are settling, the wood pigeons gone quiet, the distant traffic faded to almost nothing, the air cooling quickly now between the trunks. The robin does not move. It is oriented southwest, its body angled in a direction that has no visible marker in the darkening tree line, no landmark, no star yet risen, no feature on the horizon that a watching person could point to and say, "There, that is what it is facing." The direction the robin holds is something it carries from inside, and what it is carrying is the specific pull and tilt of the magnetic field passing through the place where it stands. The signal it is reading is not loud. It produces no detectable sensation in any human body standing nearby, no needle trembling on any instrument left open on the forest floor, no variation in the quality of the autumn air. The field is simply there, as it has always been, moving through the bark of the branch, and the leaves still clinging to the oaks and the small body of the bird, and the bird through a mechanism so quiet it took biologists decades to locate and describe, is reading it. In the cells of the robin's eye, there are proteins called cryptochromes. When light enters the eye and strikes these molecules, electrons are briefly knocked into a state where their quantum mechanical properties, specifically their spin, the deep internal orientation of the particle itself, become sensitive to the direction of the ambient magnetic field. The cryptochrome molecules, in effect, function differently depending on which way the field is pointing, and that difference translates into a signal the bird's nervous system can use. What the robin experiences is not understood. Whether it perceives the field as a color, a brightening, a pressure, a direction felt in the body, the way warmth is felt, none of that is knowable from outside. What is known is that the robin orients correctly, that it does so using its eyes, and that the chemical process behind that orientation is sensitive enough to work in fields as gentle as the one threading through this forest on this particular October evening. The bird holds its bearing southwest. It will fly tonight, or tomorrow night, or in the night after that, following the same direction for hundreds of kilometers until it arrives at wintering grounds in southern France or the Iberian Peninsula that it has never been to before, at least not in this direction, not in this year's body. It will find them not by watching the stars alone, not by following other birds, not by reading any landmark the human eye would recognize at altitude in the dark, but by carrying the field with it and measuring its own position against the only map it has, which is the invisible architecture of the planet's magnetic lines running from somewhere behind it towards somewhere ahead. Studies that tracked individual robins and other migratory passerines near zones of elevated magnetic field gradient, places where the local geology or volcanic history produced a sudden change in field strength over a short horizontal distance, found that the birds respond measurably. Increased circling, reversed headings, held briefly before correction, a period of recalibration that shows up in the track data as a small loop or an extended pause at a consistent geographic location. The birds are not lost. They are, in a more precise sense, rechecking. The same animal that navigates unerringly across 1,000 kilometers of continental Europe can be momentarily thrown by a patch of magnetized rock 100 meters wide because the field it reads has briefly said something inconsistent with the map it is carrying. The inconsistency resolves. The bird corrects. It continues. The robin on the German branch sits for another moment, then launches into the air without visible transition, climbing above the tree line, disappearing into the broad dark to the southwest. Its passage through the field is something that leaves no trace. Deep inside a beehive somewhere on a warm hillside, a honeybee is dancing. The hive is housed in a wooden box in an apiary, the individual combs suspended in frames, the interior warm and faintly vibrating with the collective sound of many thousands of bees going about the work of the colony. On one of the vertical comb faces, a single forager is running a figure-8 pattern on the wax surface, the waggle dance, as it has been called since the mid-20th century, when the Austrian ethologist Karl von Frisch worked out its structure through careful observation and methodical experiment. The bee runs a short straight line at an angle to vertical, vibrating its body rapidly along the run, then circles back in a wide arc, runs the straight line again, circles back in the opposite direction, and repeats. The angle of the straight run, measured against the vertical axis of the comb, encodes the direction to a food source relative to the sun's current position. The duration of the run encodes the distance. Other bees gathered close are reading the dance and calibrating their own flight plans in response. What von Frisch had established by the early 1970s was one of the most detailed accounts of non-human communication known in biology. What later researchers found added a further layer to an already intricate picture. Honeybees carry inside their abdomens chains of tiny crystals made of magnetite, the same iron oxide mineral that concentrates in the crustal rock formations capable of disrupting a compass. The crystals in a bee's body are not a navigational instrument in the way the cryptochrome network in a robin's eye appears to be. Their role is still an open question in biophysics, but their presence means that the bee's body is sensitive to the ambient magnetic field in a direct mechanical sense in a way that is measurably different from the quantum chemical sensitivity of the bird. Controlled experiments have shown that artificially applied magnetic disturbances, fields imposed on a hive from outside using electromagnetic coils, alter the waggle dance in quantifiable ways. The angle of the straight run shifts, the precision of the direction encoded in the dance degrades. Bees that were consistently indicating a food source at one bearing begin to indicate it at a slightly different bearing, consistently in a pattern that follows the disturbance applied to the field rather than any change in the actual location of the food. The communication system is functioning correctly relative to the field it is measuring. The field is simply being told something that does not correspond to what is actually out there. The sensitivity threshold of the honeybee's magnetite system has been measured at around 26 nanoteslas. That is the magnitude of change in field strength the bee can detect. It is a very small number in absolute terms. The Earth's ambient field ranges from roughly 25,000 to 65,000 nanoteslas, depending on location, which means the bee is detecting changes at the level of a small fraction of the background field. It is not, however, a small number relative to the variations that real rock can produce. A magnetite-bearing outcrop at the surface of a hillside, a cluster of iron-rich intrusive rock in a hillside the bees happen to fly over daily, a stretch of mineralized soil in a pasture between the hive and a known flower meadow. Any of these could produce a field variation at or above the threshold the bee's system responds to. The bees navigating across that terrain would be working in a field that says slightly different things in different places. The dances they perform on return would carry that information or that inconsistency into the arithmetic of the hive's collective map. The bee on the comb surface completes another figure 8 and starts again. The bees nearest to it read the angle of the run and make their adjustments. The hive continues its work. The field threading through the wooden box of the hive does not change tonight, and the dances encode the bearing correctly, and the foragers that leave in the morning will find the meadow exactly where the dance said it was. A loggerhead sea turtle hatched on a beach in Florida sometime in the last quarter century. The hatching happened at night, which is standard for loggerheads, the emergence time to the cooler sand temperature of darkness and the lower risk of predation that comes with it. The hatchling moved down the beach in the direction of the water, following the natural light gradient of the open ocean horizon against the dark landward sky, and entered the sea at the edge of the surf. What happened in those first hours and days of ocean swimming, before the turtle settled into the North Atlantic gyre, is not directly observable in any individual animal. What is known is that somewhere in that early period, the geomagnetic signature of the natal beach, the specific combination of magnetic field inclination and intensity that characterizes that particular stretch of Florida coastline, was encoded in the turtle's nervous system as a remembered address, an address with no words, no numbers, no coordinates in any human system, an address written entirely in the language of the field. Loggerhead sea turtles can live for decades. A female does not return to breed at her natal beach until she has reached sexual maturity, which takes between 15 and 20 years, sometimes longer. In the interval, she will travel tens of thousands of kilometers through the Atlantic and Mediterranean, feeding and foraging grounds far from where she was born, moving through water that looks identical in every direction and carries no visible trace of where any particular beach might be. When the time comes to return, she does not look for the beach, she looks for the field. The B-coordinate magnetic map hypothesis, which has accumulated substantial experimental support over several decades, proposes that the turtle uses two independent magnetic variables: inclination, which is the angle at which the field lines dip below the horizontal, and intensity, which is the overall strength of the field, as a pair of coordinates that together narrow a location on the Earth's surface to something a migrating animal can aim for. No single variable is sufficient. Inclination alone produces a band of similar values running roughly east to west across the Atlantic. Intensity alone produces a different band. The intersection of the two values is, however, much more specific. By measuring both and navigating toward the remembered combination, the turtle can home in on a geographically restricted target from any starting point in the open ocean. The complication that arises in this system is that the geomagnetic field is not fixed. It moves, not quickly, and not in ways that reshape the planet's large-scale magnetic structure in any given turtle's lifetime, but the small-scale details of the field at any particular location shift slowly over years and decades as the field's secular variation unfolds. The magnetic address of a Florida beach in the year of a turtle's hatching is not precisely the same as the magnetic address of that beach 20 years later. The difference is small, but a sea turtle navigating to a specific magnetic coordinate will find the location where that coordinate now exists, which may be slightly displaced from where it was when the turtle imprinted. Research has found that nesting distributions along Atlantic coastlines shift in ways that track these slow magnetic displacements, the nesting population following the address rather than the geography, arriving at the coordinates that match the remembered field, even when that means a slight offset from the historical center of the nesting range. The navigation works as designed. The field moved, and the turtles moved with it. Somewhere in the deep mid-Atlantic tonight, a loggerhead moves through water that is between 12 and 18 degrees Celsius, at a depth that is dark enough that no sunlight reaches it, in a direction that has not changed for several hours. The field is there around it, inclining at the angle it inclines at this particular latitude and longitude, carrying the intensity it carries here, distinct in both values from where the turtle was yesterday and distinct again from where it is going. The turtle reads both values simultaneously, and the reading is the navigation, and the navigation continues through the long middle of the night. Along the coast of the North Sea, the cetaceans known as pilot whales move in groups that can number from a few individuals to several dozen. They are social animals, highly organized, with complex relationships within the group and communication that involves sequences of sounds, specific enough that different groups have been observed to carry different acoustic repertoires, regional dialects in the loose sense of the term. Though what the whales make of the distinction is not a question biology has answered. They are deep divers, capable of descending to more than 500 meters in pursuit of squid, and they navigate over large areas of open ocean using a combination of echolocation and, it appears, geomagnetic sensing, though the precise mechanism in cetaceans is less well characterized than in birds or sea turtles. In the 1980s, a researcher named Margaret Klanowska examined the geographic distribution of live cetacean strandings along the coastline of the United Kingdom, the events in which living animals, or animals that were alive when they arrived, came ashore in shallow water and could not return to sea without human intervention. She found a statistical pattern that was not in the data she had expected to find. The live strandings were not distributed randomly along the coast, and they were not distributed according to the features of coastal geography that might be expected to trap a navigating animal. Bays, inlets, shallow shelving beaches. They were concentrated at locations where the magnetic field contour lines, the lines of equal field intensity, ran perpendicular to the shoreline. At locations where those lines ran parallel to the shore, strandings were rare. The hypothesis that arises from this pattern is that the whales were following geomagnetic gradients inward, navigating along lines of decreasing or increasing field intensity, using the gradient as a path. In open ocean, this is a useful and reliable guide. A geomagnetic gradient running in one direction leads continuously through water to more water, and the gradient leads back outward the same way it led inward. But where the gradient runs perpendicular to a coastline, following it faithfully will eventually deliver the animal to shallow water. The navigation system has not failed. It has succeeded precisely. The gradient was there, and the animal followed it, and the gradient ran all the way to the sand. The pattern Klonowska found has been re-examined and debated in the decades since, with some studies finding support for the geomagnetic correlation and others finding it insufficient as a sole explanation for stranding distributions. The picture that has emerged is not a clean single-cause account, but something more complicated, a combination of factors in which the geomagnetic landscape is one contributor among several, including disease, social cohesion within the group, and the behavior of prey species. A whale following a leader or following prey may follow that path to a beach regardless of what the magnetic field is doing. A whale navigating independently through coastal water in conditions that make echolocation unreliable may rely more heavily on the geomagnetic gradient than it otherwise would. The strandings that result look the same from the outside, and the field's role in any particular event is not directly readable from the outcome alone. What is clear is that the whale is operating within the same invisible geography that the robin and the turtle and the bee are operating within. The field that runs through the water in the North Sea on any given night is read by many bodies at once, each body applying it according to its own biology, each finding in the same signal a different set of useful instructions. The sockeye salmon moves through coastal Pacific water in late summer and early autumn, its body changed over months of ocean feeding from something silver and built for open water to something red and altered, the jaw reshaping, the fat reserves built for the long push upstream. It is navigating toward the mouth of a river it has not entered since it was a juvenile, small enough to be carried for a time on the current, rather than swimming against it. The river it is looking for is the Fraser River in British Columbia, one of the largest salmon rivers on the Pacific coast of North America, its annual return of sockeye, one of the most studied migration events in fish biology. Research published in 2013 examined a long-running puzzle in Fraser River sockeye returns, the fact that fish approaching the coast did not all arrive at the same entry point. The Fraser River meets the sea at two possible approaches, one that runs south of Vancouver Island through the Strait of Juan de Fuca, and one that runs north of the island through Johnstone Strait. In different years, the proportions of fish taking each route varied considerably, and the variation did not correlate cleanly with any of the obvious candidates: water temperature, prey distribution, fishing pressure, or river flow conditions at the mouth. What the researchers found was that the variation in route use correlated with the long-term, slowly drifting position of the oceanic magnetic field in the Pacific coastal waters off British Columbia. The geomagnetic field in that region, like all regions, has been shifting gradually over the decades of the study period, its intensity and inclination values changing at rates measurable only across multi-year or multi-decadal timescales, too slow to be perceptible to any single salmon in any single migration, but detectable in aggregate when route choice is tracked across populations and years. The population level data showed that as the field shifted, the population level preference between the two routes shifted in correspondence. The fish were not following a learned route or a culturally transmitted preference. They were following a magnetic map, and as the map moved, they moved with it. What this means for any individual salmon is that it arrives at the coast carrying the magnetic address of its birth river, encoded somewhere in its biology, and it navigates toward that address through coastal waters where the field values it is reading change slowly with the seasons and the decades. It has never seen a map. It does not know the coast. What it knows is the field, and the field processed through whatever sensory system the salmon uses, which likely involves magnetite crystals in the lateral line or the olfactory organs, though the precise receptor remains an active area of investigation, tells it which direction to go, and it goes. The salmon moving through the coastal Pacific at dusk are in water that is cold and green, visibility dropping quickly in the late season light, the surface broken by a moderate swell. They move in loose aggregations, many fish in proximity without the tight schooling behavior they showed as juveniles, each individual holding a general heading that is not quite the same as the heading of the fish beside it, a spread of directional responses averaging across the group to something very close to the magnetic bearing of the river mouth. They are close now. The field values they are reading are beginning to match the remembered address, closing in on the specific combination of inclination and intensity that encodes the Fraser River Delta from the coastal Pacific. They will find it. They find it every year. There is a quality to the way the magnetic field operates on the living world that becomes clearer the longer one considers the range of animals that use it. The field is not a signal in the way that sound or light is a signal. It is not emitted by any one thing, received by any one receptor, carrying any message in a conventional sense. It is a property of the space the animals move through, a continuous invisible medium that fills the ocean and the forest and the air above the prairie with directional information that most of the organisms moving through it are reading constantly in ways that range from the quantum chemistry of a bird's eye to the tiny suspended crystals in a bee's abdomen to the map encoded in a sea turtle's nervous system during its first hours of life. The field is also not static. It has a large, slow drift built into it, the secular variation of the planetary dynamo, the gradual wandering of the magnetic poles that has been measurable since the first systematic geomagnetic surveys of the 19th century. And it has the smaller, sharper variations produced by the mineralized rock of the crust, the anomalies where iron-bearing stone adds its own contribution to the planetary signal, producing field values higher or lower or directionally different from what the global model would predict at that location. The animals navigating through these regions are navigating through a landscape with texture. The texture is invisible to almost everything with eyes, but it is perfectly legible to the chemistry that reads it. A migratory bird crossing a patch of strongly magnetized bedrock is passing through a small zone of field inconsistency, a place where the global map has a local edit written in stone. The bird corrects and continues. A loggerhead sea turtle, following a magnetic gradient toward a remembered address, is following a thread through dark water that has been slowly moving for its entire life, the destination always slightly ahead of the current reading, the gap closing. A bee dancing in a hive near a hillside of magnetite-bearing serpenite is encoding directions into the dance using a field that says slightly different things in slightly different places above that hillside, and the foragers that follow the dance are flying through those variations and noting them, and in some complex way that is not fully mapped, the hive's collective knowledge of the landscape includes something of its magnetic texture. The blue whale moves through the open ocean, the deepest water, the widest range, the least studied navigation of any of them, and it is reasonable to expect, given what is found in smaller cetaceans, given the presence of magnetite in whale tissue samples, given the distances involved, and the reliability with which whales have been tracked, returning to feeding grounds year after year across featureless open ocean, that the field is part of what it reads. The mechanisms are not described in the same detail as they are for the robin or the turtle. The research has not reached as far into the whale's sensory biology, but the field is there around the whale as it moves through the dark water, and the whale is moving through it with purpose, and the distance between what the field is and what the whale makes of it is a gap that is slowly closing in biology, the same way the magnetic address closes for the loggerhead, incrementally, over long time, with the direction held. The European robin in Germany has been airborne for some time now. It is moving through darkness above a landscape it cannot see, in detail, the forest below it, then agricultural fields, then the low hills that precede the Rhine. The field it is reading changes in small ways as it moves. The inclination shifts by fractions of a degree per 100 kilometers. The intensity changes by a number of nanoteslas that the cryptochrome system in its eye translates into something it can use. The changes tell it where it is relative to where it is going. The field ahead is slightly different from the field where it currently is. The field at the wintering grounds in southern France or Iberia has a specific character, and the bird is navigating toward that character through the dark. And the dark is not a problem because the map it is using is independent of light. It crosses the Rhine without knowing it is the Rhine. It crosses into France without knowing it is France. The borders and the maps and the navigational systems that humans have built over centuries to describe this same territory are invisible to the robin and unnecessary. What the robin has is the field, and the field describes the territory in a language that does not use any of the names. There is something genuinely restful in this, considered from the outside, not because the animals are unaware of the complexity of what they are doing. That question cannot be answered from where we stand, but because the navigation is in a sense already done. The address is encoded. The map is the field. The field is everywhere the animal needs to go, and the reading of it is continuous and largely automatic, a process that does not require effort or decision in the way that consulting an external instrument requires effort and decision. The robin does not stop to check. The turtle does not pause. The salmon does not compare readings against a reference model. The field tells them what it tells them, and they go. Somewhere in the central Pacific, a loggerhead sea turtle is moving at a depth of 40 meters in water that is dark and cold and very still. It has been at sea for more than a decade. The Florida beach where it hatched is not in its experience as a memory of place. The smell of the sand, the angle of the dunes, the temperature of the water at the edge of the surf. None of those sensory details are accessible to it at this depth in this water at this distance. What it carries is the field, the inclination angle of that beach at that latitude and longitude, and the intensity value that characterizes the coastal water there, encoded in some combination of neural response and magnetic sensitivity that remains one of the more quietly remarkable open questions in comparative biology. The turtle is not in any distress. It is not searching. It is moving through water that at this moment does not yet have the magnetic character of home. That character is ahead, in a direction the turtle is already holding, in a field that is already beginning to change in ways that the turtle's body is already noting. The change is small, a fraction of a degree in inclination, a few nanoteslas in intensity, but it is in the right direction. The address is getting closer. The field ahead is becoming more like the remembered field, slowly, across hundreds of kilometers of open ocean, and the turtle is moving toward the place where the two will coincide. The sea around it is vast. The surface above it, 60 meters up, catches starlight that does not reach this depth.